Hello everyone, I'm so honored to introduce our work to you. As the title shows, this paper expects to utilize feature hallucination to realize few-shot recognition. Considering that some listeners know little about few-shot learning, I will give a brief introduction to it before explaining our work. Generally, few-shot learning aims to enable machines to learn the concepts from limited labeled set. In few-shot learning tasks, the categories of the training set and the test set are completely disjoint, and very few labeled samples for each category are provided during the testing stage. For example, we are provided with 3 categories of samples: cat, dog, and rabbit, and only 3 samples per category are labeled. We can call those 9 labeled samples spot sets and expect to correctly recognize the remaining unlabeled samples just based on the spot set. Of course, the query set shares categories with the spot set, and this kind of task can be called 3-1 task. In order to highlight the effectiveness of our proposed measure, we choose a simple cosine similarity-based classifier spaceline. As the name suggests, it uses cosine similarity between features and a weight vector to calculate the score for each category. The overall structure of our work is shown in the figure. It mainly contains 4 modules: feature extractor, distribution encoder, feature decoder, and classifier. Here, we utilize a 3-3-shot task mentioned before to describe the data flow during the testing stage. After giving a spot set and a query set, our model needs to fit all spent samples into feature extractor and obtains feature embeddings, and then divides spot features into several clusters according to their categories. Here, we combine the distribution encoder and feature decoder as generative measure, and utilize it to augment the spot set. Finally, we can use the combined spot set to fine-tune the cosine classifier, and recognize query samples by the final classifier. By the way, the reason why we only introduce the testing process is that the training process is similar to the testing process, and the difference between them are mainly in the generative measure. The core idea of our generative measure is to construct a low-dimensional latent space to constrain samples of the same category within a multivariate Gaussian distribution by variational inference, and to generate new feature vectors by random sampling in latent space. It has been proven in many works that Gaussian distribution is very suitable for describing the distribution of samples. As shown in the figure, the encoder is able to output a set of distribution parameters based on the feature vector, and we fill the parameters through the formula in the red dotted box. On the other hand, the parameter estimation method based on the maximum likelihood is more effective when the number of samples is sufficient. Thus, during the training stage, we utilize both spot set and query set to estimate the prior distribution and expect that the posterior distribution can approximate the prior by KL divergence. Follow the above encoder. Feature of the same class can be mapped into a pair of distribution parameters. The generation process is very simple. As shown in the red dotted box, we just need to use decoder to generate features based on latent vectors randomly sampled from the latent space. In order to make sure that the generated samples have discriminability and diversity, we set up reconstruction loops and classification loops to constrain the decoder during the training stage. To prove that our work has obtained the state-of-the-art results among augmentation-based algorithms, we take average accuracy over 1-shot 5-way and 5-shot 5-way tasks as the performance. The left table reports the results on many ImageNet. Results show that our work performs better than baseline and many representative methods. When combined with other augmentation-based methods, our work performs better than all methods with the 5-shot 5-way setting. Similarly, the right table shows the results on CUB. From the results, we can observe that our work can get the state-of-the-art results both on 1-shot tasks and 5-shot tasks. In order to prove the effectiveness of each component of loss function in generative measure, we utilize TSNE realization tool to show the distribution sets of samples in the filter space with different loss function. With reconstruction loops and classification loops, all generated samples are concentrated near one point because the variance of classes will gradually disappear without KL divergence. With classification loops and KL divergence, there is a clear gap between the generated samples and the real samples because the link between latent space and feature space cannot be established without reconstruction loops. And finally, only with all loss function can measure generate suitable features, which have similar distribution characteristics as spot features. Okay, thank you for your listening. If you have any questions, please contact us by email.